Good morning, everybody. Uttam Sahab and all, all my friends from Center of Modeling and Simulation. My topic today is flight simulations for satellite launch vehicles. The way we do it in Vikram Sarabhai Space Center, and actually this this talk I had given once earlier also, but they're long back in Center for Modeling and Simulation. But since the audience is new and I have made some innovations also in this, so I thought it's worthwhile repeating it. Now, another thing is that since there are some of us, like especially Uttam Sahab, who doesn't have much background in simulation, so I thought I'll also give a background on what, even though all of you are very well aware of what is meant by simulation, but for the sake of generalization, I'll put that also. Now I'll start with a launch, just the beginning of a launch, to show that okay, the launch takes place and it's in public view, but what goes behind the scenes in the launch is something which is this is the PSLV C-37, in which 104 satellites were launched.
6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3, 4, 5, 6 of normal, 7.
This is what we see, on Doordarshan every. But then, what happens behind the scenes is a few months of work. So, in which simulation is a very important part. So, this is how I have structured the presentation. Now, what is simulation? Need for simulation? I am sure most of you are aware of what is meant by all this. How do you use simulation design process, advantages and applications, and what we specifically do is NGC simulation, that navigation, guidance and controls. Now, if we come to what is simulation, it's the process of obtaining a model for a physical system and for conducting experiments with the model to understand the behavior of the system, improve the performance system if required. It is a science and an art, because I'm sure you understand that while mathematics will make it a science, but how to use it will make it an art. Advantages, that is something which, as we see it, a thorough understanding of real physical system can be obtained through simulation. Its behavior in response to a wide range of inputs and disturbances can be studied, and system can be improved by making design changes. Failure conditions and limits of operation could be defined. Process being simulated could be slowed down. Supposing it's a very complicated system, suppose it's a chemical process which takes place in real time, you can't stop it. But if you simulate a chemical process, you can step through that, each step what is happening, and understand the system better. On the other hand, also we can accelerate it to get a global picture, and you can do it any number of times without fear of degrading the actual system. And performance of real system could be, when we come to the real system, we could check the real system against projected performance parameters, which again we get through simulation only. Actual process could be hazardous, especially in the case of propellants and all, just very hazardous systems. We can, through simulation, we can at least get a picture of how hazardous or how it could be improved. You can make mistakes. You can afford to make mistakes and correct them before you actually put the fire to the rocket and let it go. And innovations we can always study, of course. There are some disadvantages also. It is totally dependent on the model which we create. If the model has any mistake, then our simulation is not going to be correct. And if you don't have a accurate enough model, which is simplified model, supposing you could make grievous mistakes in that, and that could be hazardous. It could be really bad. And finally, the proof of the pudding is that it cannot really, I mean, you can do any number of simulations, but the real test of a rocket comes in when it gets launched only. So it cannot exactly replicate the system, the physical system. Now, in launch vehicle development, how simulation is used? As I wrote in the abstract also, that the process of simulation starts from the day you define the mission. The mission is defined on the on paper and pen, and you sit on the computer, do extensive simulations, see how the mission should be defined. The government or somebody will only tell you that, okay, you launch a rocket, you launch a satellite, but how heavy is the satellite, what are the dimensions, how we are going to go about doing it. So all that we have to predefine, and that is only by doing this trajectory simulation. Now, life cycle of a flight simulation is like this. What we are told is only a mission requirement to inject a certain payload in a defined orbit. With that, first level of simulation is to work out the vehicle size and propulsion system. That is depending on the payload requirement, what sort of vehicle, whether it's a GSLV or a PSLV or PSLV, there are so many types, there is core alone, there are so many things are there. So that is defined, the propulsion system, and the trajectory, how we are going to reach the trajectory. And based on this, we find the optimum guidance technique, control law to achieve vehicle stability, dynamics of the vehicle, and the navigation guidance control system configuration. So all this is the beginning of any mission. And the end of the mission, which is just a few hours before launch in Sriharikota, is the requirement that the winds which are there at that time should be very accurately known, because they will define whether the launch vehicle is going to fail or not. So it's something called day of the launch wind biasing that we started about 10 years back. So just a few hours before launch, balloons, meteorological balloons are launched. They go to a height of about 70 odd kilometers in Sriharikota, and from that we find the wind velocity, wind profiles, and that is loaded into the flight computers as the final data. And this helps in reducing the loads on the rocket, the aerodynamic loads, and saving the mission. So many things advantages are there in this. So what I am trying to say is that from the day you define the mission to a few hours before launch, simulation goes through every bit of it. So it's something like 6-month cycle in which everything goes through simulation at different levels. Okay, now we are talking of simulation. Now simulation software, this is they call it a 6D simulation software package, which models the vehicle's linear and rotational characteristics. That is, finally, what we see in the rocket is its acceleration and its rotations. So these are and the inputs to the rocket are the propulsion system. So from propulsion to linear rotational rates, that is the job of the simulation software, simulating the complete launch vehicle in a way. Now, what is the objective of this simulation software package? the simulation, the idea is to validate a navigation guidance control system hardware and software. It is done in two parts. One is called autonomous simulations, which is numerical simulation, which we are all doing in this place, in which everything in the launch vehicle as well as the navigation guidance control system is also modeled. Both are in the computer. They interact with each other to give you results. That's the autonomous simulation. Or the other thing is with the actual hardware which is going to fly. With that you do simulations. So these are various different levels of simulation which we do. You can see it. The launch vehicle simulations. Do we have a pointer here? Okay, no problem. So basically useful for configuration finalization, subsystem finalization, algorithm design and mission planning. If you want to, we'll just see what there are so many different parts of this system modeling. There is a there is an environmental model which will which is used in the simulation package. Then there is a gravity model. There are vehicle systems, aerodynamics, mass, center of gravity, moment of inertia. So many things are there in this. Then the vehicle and trajectory dynamics, sensors, and NGC, control power plants. All these are modeled in our simulation package. So the total system comes like this. There is a vehicle system, forces and moments are the inputs to that. Other inputs are environment and gravity, which are the disturbance inputs. Control, they go to the control power plant. The navigation guidance on autopilot senses it, and that's how the loop is closed. Why are NGC simulations necessary? That is simulations using the actual navigation guidance control hardware. That is because there are too many non-linearities in the system. There is a control system which is predominantly non-linear. While if we are simulating in a computer, we have 64-bit arithmetic, but that doesn't happen in case of onboard computers. So limitation of the onboard computer is there. Interface between different systems which cannot be modeled at all. And when you integrate the whole thing, there are some delays and such things which cannot be modeled. And the vehicle stability will be seen only when you are in a closed loop. So because of these reasons, we have to go through simulations with the actual NGC systems. Now this is carried out at different levels. So we have these are the four different levels we are carrying out the NGC simulation. The first is the flight software evaluation tests, in which we are still not using the flight electronics, but from this onboard processor in the loop, we start using the flight computers and the associated instrumentation put in the loop. Actuators, the next level, the actuators in the loop, and then the complete end-to-end hardware in the loop, for which we are defining different test beds, because the same test bed cannot be used for everything. Now another thing which has come up in the real-time simulation in closed loop, Why are we requiring the real-time systems? That we can understand from here. See, if you look at a launch vehicle, when it is moving, it has got some rates and some rotations and acceleration that is sensed by a navigation system, which gives input to the guidance system, which tells the guidance system tells the launch vehicle how to reach where it has to reach, and that gives input to the control system and sequencing for staging of the this thing, and so the commands go back to the rocket. Now the thing is, in this, it's an active control system, and there is an active rocket, and if the control system, there will be delays in this. If that is they are not taken care, then the whole thing is going to become unstable and the launch will fail. So that is why it is a real-time system is required to simulate this. That is, in real time, the simulation software is going to accept inputs from the control and sequencing. Navigation system has got the inertial sensors, that is gyroscopes and accelerometers, and the processing electronics to give you. Gyroscopes will only sense the rotation rates, but from that finding in the instantaneous angular position and rate, of course. Then the accelerometers will sense only acceleration. From that you integrate to get velocity, double integrate to get position. So position, velocity, acceleration, rotation, attitude and rotation rates, these are the outputs of navigation system, and this is in for the use of the control loop, it is in spherical coordinate systems, but for giving to the general public, it's in latitude, longitude and altitude. So all that work is done by the navigation system. It gives input to guidance, which there is a guidance law which which tells from the immediate location to the final point where in the orbit where it has to reach, how it's going to reach over there, what is the most desired optimum path which is going to take to reach that point. And that is not done once, that is done continuously during the flight, because depending on the propulsion characteristics, the location will not be as we had defined in the beginning. That difference comes because if you have open loop guidance, then from that point to that point you have only one algorithm that will work. But when you have closed loop guidance, then this will be calculated every instant, every 20 milliseconds and updated. See, we are talking at different levels. When we start a mission, we start talking about a mission, that is defining a mission, that time nothing is known, except that you have to put something in an orbit. From that point onwards, the orbit has all you know is that from Sriharikota it has to be launched, it has to go into 400 kilometers circular orbit. Where in the circular orbit has to reach and how it's going to reach over there, that is defined in what you say numerical simulations, what we call autonomous simulations. Once all that is defined and frozen, with that only you can freeze the software in the flight computers, and with that only we'll start doing these onboard computers and loop simulation and NGC systems. So it is not that your mission is unknown right till the end. No. Once a mission is defined, it is frozen and it is loaded in the flight computers. The guidance scheme for that is loaded in the flight computer. And also control system also depends on what is the characteristics of these control power plants. Based on that only control law is also defined. Real time, that's what I was saying, that launch vehicle dynamics demand control system to be commanded at a definite rate, otherwise it will become unstable. So flight computers which do the navigation guidance and control for launch vehicles receive these inputs from navigation sensors and provide control command to the actuators. This is done based on real-time executive software operating system in the flight computers. Since NGC sends commands in real time and expects inputs in real time, so the simulation has to work in real time. Okay, it is all done in. So there is a difference between when we do a numerical simulation. Time is not a criterion at all over there. This system runs, the simulation software runs, and the navigation system also runs, and they interact with each other. But in this case, when the real flight articles are used, then since they are working in a real time, the inputs also have to come in real time. The simulation and the NGC, they are working in a synchronous fashion. Let's start with the simulation. You can see there is a data acquisition window, and once data is acquired in the simulation computer, the computation, and then data is sent down over here. So this data is acquired over here and generates the control commands. So there is a 1 cycle lag between the simulation and the NGC. This is the time instant, incremental time, cycle x plus 2, x plus 1, x, like that. So data which is actually control data which is sent at this point, a command corresponding to that comes only 1 cycle after that. But this is not a problem in the simulations, in the simulation software. It happens in the real case also. That whatever data is generated, it is used 1 cycle later. There have been times when our simulation computer has not worked properly. So we did not get the data at this point. We got at the x plus 3. So I mean, it shows a lot of delays and a lot of instabilities which were actually not there. And when we came down to finding out why, we found that the simulation computer, it was a new thing which we had bought. It was having some inherent delays, and there we had to cut it out. So this is how closed loop tests are carried out for NGC. So now we come to the flight simulation, real-time simulations. So we have a simulation computer which has got all these models in it. That is the sensor model, center of gravity, moment of inertia, gravity, aero, flexibility is something new which we have included now recently. Disturbances, propulsions, actuators, which talk to the navigation to the onboard computers through an interface. And then we have the flight systems over here. At a more gross level, you have the simulation system, which is one computer. There is the flight computers, and then the checkout and data acquisition on the other hand. So this is our total assembly of our simulation lab, you can say. The checkout is required to power on all these flight computer systems to initiate the flight, and start synchronizing it with the simulation computer. These simulations are done to evaluate mission performance of each element within allowable bands, ensure correct interface between elements, flawless function of each element in the integrated configuration in the flight under expected flight environment, and ensure no failures. Methodology is in a stepped fashion replace the mathematical models of the NGC with the actual flight article. So initially, as I said, we have got tests which are done using only the onboard computers. Then we introduce the control power plants, and then we introduce the inertial sensors. This is the our simulation test bed, and here also we have one test which we do, which is called a okay, we'll come here. One very important thing which is done is the NGC software stress test. The thing is, since the first PSLV failed because of a software bug, so we are extremely wary about the software errors which could creep in into the system. And our, in fact, simulations started on a grand scale only after the first PSLV failure. So disturbances are provided to the onboard software, not just in a plus minus 3 sigma sort of environment where winds and propulsion, everything varies within tolerable defined limits. It goes to unexpected disturbance. That supposing there is a failure, in which case you will not be able to restrict your disturbances to only plus minus 3 sigma. It could go to much more than that. Something like suppose you are expecting some X amount of dispersion, we give 5x disturbance and see whether the onboard software is able to save itself. The thing is, even if there is a disturbance coming, is it going to damage the vehicle or what is going to happen? So the onboard software is made so robust that any amount of disturbance, it is not going to cause any disturbance, any failure to the launch vehicle. Launch vehicle may fail because of some other different reason. It has happened also earlier, but software is not going, or navigation guidance control system by its operation is not going to cause a failure in the launch. That we ensure by doing these simulation tests. Now, I wanted to digress a little bit. How quality software, that is one thing which we have worked out. What is a quality software? What are the characteristics of quality software? It should be free from algorithmic or logical errors. It should be robust. It should be able to handle large range of input data with disturbances without malfunction. It should be durable. It should be capable of operation for different applications without having to undergo large scale modification. In fact, PSLV, whatever we made for PSLV D2, that is the second launch, first launch failed, second launch it made, it is still working after 40 launches. There is a durability and versatile. It should be able to function across variety of platforms. That is, whether you are initially we were working under DOS, then we came to Windows, then we came to Unix, so many different things are there, but the basic simulation software has remained the same. Now, oils. The other one thing was the software test bed for flight software. This is again, once again, steps. This is another thing which we are doing without using the flight packages, and this is once again to do a very high stress test on the flight software. Onboard computer oils is basically a workhorse which is used from the time the flight's article is defined to the time you launch for the DOL also. So that is a thing which is used, because there is nothing in this which can go bad, unlike any actuators or control sensors or inertial sensors. Nothing can go wrong in this. Then the actuators in loop simulation. where the uh, the flight control power plants from different stages are assembled in our lab and interfaced with the onboard computers this, and the simulation computer to see their function, see the function of the whole thing with the actuators. And the hardware and loop simulation, which is the simulation with the inertial sensors also. That is difficult because inertial sensors means till now you were able to, the simulation computer was able to give rotations and in a mathematical form, but when you have the actual sensors, you need a physical, something which moves to rotate the gyroscopes. So for that we have angular motion simulator like this, which is 3-axis motion simulator on which the navigation sensors are mounted, and this is interfaced to the simulation computer, and so the whole cycle is repeated like that. This is actually one place where the complete the NGC system is integrated together. So this is in a way a final test before the navigation systems are assembled and shipped to Sriharikota for integration in the launch vehicle. Actuator loop simulation also is not the not because the inertial sensor are not included. And this is also tried, this is a complete vehicle in the loop. But this has its own limitations because everything, if you have the motion simulator over there, that has its own dynamics, control systems have their own dynamics. So this is not, this is only a final test which just shows everything is working fine, everything together. So this is how we are doing the simulations for the launch vehicles.